some more definitions and assumptions, because what we need to do now is, we know this guy, this is the randomness, n bar is the mean of your ith detector at jth angle. So this is the randomness, right? First, when we start with, this is the randomness that starts, your n is a random variable. So now what we will say is, for simplicity, we will assume that Nij is independent. Okay, what is happening in one detector, one view, need not affect the other one. So we will take this independent assumption, which is not that bad, okay, which is okay. Assume Nij is independent for different measurements, and then you say Nij equal to n, that is, it's the same, mean is same. When will be the mean same? Number of photons that are coming through, when will it be same? Oh, if I have a homogeneous medium, then I can expect whatever I sent in and whatever I receive in each of the detector for different views, at least for within one view, right? If it's a symmetric object, it's a circle, then for all the views, they all have to be the same value, right, on an average, the average value. Why? Because it's a homogeneous attenuation. In such a case, we can, it's okay for the purposes of understanding what all factors play a role. This is not a limiting um, uh, assumption. So we can always start with signal to noise ratio. When we do, we always talk about homogeneous medium. You have many measurements, what is the fluctuation? If the signal itself is changing, right, if you have inhomogeneity, then it becomes, you have to segregate different locations and see whether the signal and noise are correlated. So to make life easy, right, this is something that is routinely used, so it's not that bad, okay. So this is the assumption. So we can essentially talk about, doesn't matter which detector, which view angle, the mean is independent of that, okay. So you can use only one n bar. Again, CL, this filter function, for simplicity, otherwise you'll have to have Hamming window or Hanning window, you'll have to have another exponential or whatever to describe that. To make life easy, we will say this is a rectangular window, so that less of a confusion. But the idea is, you can change this, okay. But for simplicity, we will say this is a rectangular window. Okay, so this is for the fundamental n that is going in, this is the filter function. Then what is there? Oh, then there is a g, right, that goes in. So g operates on this, and that is the one that goes into the back projection algorithm. So your g, because of this, we can also assume g are also independent, okay. Just this is okay, we'll say for the purposes this is fine. If we were able to live with that, with n, g is random just because of n, and therefore this is fine, g is also independent, okay. Then the point is, we need to get mean and variance of your image, that is what we want. So we can derive this. You start with the convolution back projection, right, that is your algorithm. You have the input random variable, you have this one implemented as rectangular. So if you substitute and work out based on the assumptions of independence, right, there are few steps. Even in the text, it's not a detailed derivation, but there are a couple of more steps that are given after these assumptions, and essentially you get a expression for your variance, okay. So what is this? So the detail of these derivations are not that important for the context of this course. So even in the textbook, only a couple of equations are given just before this to capture it, and and this is okay. Why we don't want to get into the complicated derivation, because already it's simplified. In the real context, when you are working in it, you have to be very diligent, but here the objective for us is to understand the factors and relate to our instrumentation and physics. So we will not go into the details, but essentially this is an expression that you get by making these assumptions and starting out with the discretized approximation of your convolution back projection. So this is the variance you get. What is interesting here is this variance is a function directly related to your rho naught. What is this rho naught? Oh, this is your, you do your filter, right? That is your highest cutoff of your filter, filtered back projection, right. So this has to do with your cutoff of your filter, and your M is, we saw previous, is the discretization, right. So more the M is the angular discretization. So more the M you have, oh, more the M I have, less the variance, less the noise. Oh, okay, more I sample, I have less noise, right, less variance, intuitive. Okay, what is this? Oh, higher cutoff. So if I have a higher cutoff, I have higher noise. Why? Oh, if your cutoff is more, probably high frequency features are coming. So noise, lot of noise in the high frequency are coming in, and therefore you can expect the more the cutoff, maybe after some time your feature is not there, but your high frequency noise is coming in. Okay, so you have to be careful about how much high frequency you want to provide the cutoff. And then you have these guys. What is your n dashed? Oh, average number of photons, which we kind of know. Oh, increase the number of photons, you shoot more photons, right. If you shoot more photons, you will reduce the variance, which we knew from before, but downside is there, right. You don't want to send too much n. So if you send high energy, for example, you will increase n, it won't interact much, it will come out. So we talked about that. So again, it's not one way street. And then n dashed by t, so this t is actually in the numerator. So what does this say? What was your t? T was your width, right, your detector, it has to do with the detector. Okay, so so this is basically, if you, the way it is written here, number of photons per detector. If you increase the number of photons per detector, your noise will reduce. That's how it is written, that's why it is written like this. Okay, fine. So we can talk about the different variables and how it influences, increases or decreases. Increase in the cutoff and T detector spacing, right. These all increase your noise. Noise decreases when you have these two. Increased sampling, right, you have more finer views and more number of photons. Okay, so much for your noise, but we are not really interested in noise in isolation. What are we interested? We are interested in signal to noise ratio. Okay, so signal to noise ratio, what is our signal? What definition we, oh, we will use a similar definition, mean to standard deviation, right. We talked about mean as your signal and the variation around the mean is your noise, right. So we talked about signal to noise ratio as mean to standard deviation, mean of your attenuation coefficient, so it is mu bar, standard deviation, so sigma of your mu estimate. This is your signal to noise ratio in a traditional sense. However, we talked about this local differential signal to noise ratio when we covered image quality. So it is also common that because our interest is in looking at image contrast, the signal to noise ratio can also include your C, which is contrast. So it's a differential contrast. So differential signal to noise ratio is what we are practically interested, right. And so this C is nothing but your differential contrast, fraction change of mu from mu bar. So we covered this differential SNR when we talked about your image quality, introduction to image quality. So go look at that portion if you want to know what we have done here. So, this is your differential signal to noise ratio. Why? Because we want to talk about this contrast. That's interesting. Okay. So, that is your SNR. So, now what we need to do is identify. This is a big picture definition. So, what do we know? Oh, we know what the noise is. Mean is not a big deal. Mean is just mu bar. This guy, that is a problem. What is the variance? Right? We had a variance derived, right, in the previous slide. We will have to substitute that here. So, when we substitute and rearrange, you get signal to noise ratio to be C by, of course, what we had was variance, we will have to take a square root. So, you get this square root here. So, C mu bar by square root of sigma square, right. So, you get this pi square root of 3 by 2 m by, so whatever was your directly proportional, inversely proportional, right, that is kind of changed here slightly, because we wrote this as in the denominator before, at least the way we wrote it. Okay. So, what does this say? This says, okay, I am interested in signal to noise ratio and how am I affected. Fundamentally, this is important, right. Fundamentally, C is important. If there is not much differential signal there, maybe you are not going to see much, but let us not worry about that. So, this is a part that is important, but then it is this part that is going to affect for whatever you start with. This is the guy that is going to affect you. Okay. So, how do you design? What are the things that are in your control to do a good design so as to get maximum SNR, right? Things that you have in control is, oh, we talked about this cutoff. So, what could be the cutoff that we want to use? Well, without mentioning explicitly, you already know we are talking about discrete implementation, and this is kind of a right, your cutoff for this filter. So, where do you, how much frequency do you allow, right, especially the highest frequency, that is the question. So, what do you do? Oh, when you have discretization, some filtering, the first concept that comes to your mind is anti-aliasing filter, right. You should have the filter such that, so that when you do, you have the Nyquist criteria is met, right. You have to have at least twice the highest frequency, otherwise you will have aliasing, which we will talk about aliasing also as a artifact, but so here is your control. So, you could essentially design your cutoff so that it can serve as an anti-aliasing filter. So, you cut off the highest frequency, whatever you want to allow, right. After that you digitize. So, your anti-aliasing filter, you can have your rho naught to be k by w, where essentially your w is the width of the scanner. So, if you can design it like this, then you can minimize at least the artifact and you can get a good signal to noise ratio. Okay. So, that is fine. So, when you substitute that, right, when you substitute that condition, you can reduce this further to, because you had some values here, right. So, we can reduce it to 0.4 because your rho naught is substituted, right, in terms of k and w. W is the width of the scanner, so k and t, k is approximately equal to 1, so it is in terms of t. So, you can do this part and you get 0.4 k C mu, right, w square root of this guy. So, the idea is, this is your signal to noise ratio, differential signal to noise ratio. So, you can quickly look at this and convince yourself, if I want to have good signal to noise ratio, the good contrast, I have to increase my m, I have to increase my n, but there is a square root. That is the important factor. Okay. So it's not just if I want to double this SNR, I have to quadruple this. So you see in some sense this is intuitive, but then explicitly putting it makes it compelling to take that look. Okay. So that is what that is. So that is for parallel beam. So you can do the similar thing for your fan beam. When you do it for fan beam, you can talk about n suffix f as a number of photons count per fan, and d is your number of detectors, and L is the length of the detector array. So there is a slight change in the formulation because of this. So your SNR is 0.4 K C mu L n of m by d cube. Okay, so your n is your mean is your nf by d, and W is your L by d, length of the detector array by number of detectors is going to give you your width per detector. Okay. So this is fine. For fan beam you get some similar things like this. So SNR decreases as D increases. This is something that is right. D increases, SNR decreases. D is number of detectors. So this is something that is not intuitive. You would have expected if you have more number of detectors, you have more measurements, so you will probably get less noise, at least because you are averaging and right, you are reconstructing using more number of independent random variables. You would expect that the variance would have reduced, and therefore your signal to noise ratio will improve, but that is not happening. It turns out that the D is in the denominator. So it says that this SNR decreases as D increases. Why would that be? Right? Oh, what assumptions did we make? In parallel ray, we said neighbors don't disturb each other, independence. Whereas it turns out in fan beam, the convolution of the projection, right? You have this ramp filter that kind of couples noise between the adjacent detectors. So because of that, your detectors are not, say, the neighboring ones are not independent. So there is a coupling that is taking place, and therefore the noise between the detectors is coming into picture. So this effectively increases the noise. So more the number of detectors in this configuration, the detectors interference is there, and therefore your noise is going up. Okay. Of course, you can do larger D is desired. Why? D is the number of detectors. So if I have many number of detectors, right, then each one will be small. That means my resolution is good. So it's always a trade-off. That's the problem in most of the modalities. That's always a trade-off, but then if you understand enough of how each parameter is affecting, which are conflicting, which are favorable, then you talk with the clinical practitioner, you talk with the engineer on site, you kind of work out a agreeable trade-off. It's always about negotiating an agreeable trade-off. That's the important practical aspect that you will find in all of these. Okay, good. So much for SNR. So what do we want to do? We talked about resolution, we talked about noise not in isolation, noise in the context of SNR, not just that, SNR for fan beam also. So now we are good to proceed further. Just before that, in fact I won't solve this, just to appreciate, right, so that you can relate all the parameters we talked about so far. Consider a fan beam CT system, right, with one source. Let's not deviate much from what we know. So you have D detectors, M angles, and a image size is also given, J by J. So here you are treating the D equal to M equal to J equal to 256. So it's a 256 cross 256 image. So you have taken 256 views, and in each view you have 256 detector measurements. So now assume that the width of each detector is 0.25 centimeters, so 2.5 mm. Okay. and you are using a ramp filter, rectangular window, so we will not complicate that. Why? Okay, so we have also designed it such that it is 1 by d, it is anti-aliasing. So we are designed that with a cutoff that is equal to 1 by d, d is 0.25, which is your width of the detector. Okay. So now you are using the scanner to measure a lesion, right. So the contrast between the lesion and the surrounding tissue, right, is 0.005, or so this is not the scanner is used to image a lesion with a contrast embedded in water. So the surrounding is water. Okay. So your water, okay, you have your mu bar average, this thing is also given. So now the question is, okay, given this setup, this is what I want to do. You are given a constraint. Oh, I want to do the imaging, but subject to at least 20 dB I need to make any diagnosis. Only then I will be confident in saying that is a lesion is whatever it's there, and I can do follow up. So if we require the image to have SNR of at least 20 dB, what is the minimum number of photons per projection, right? So now it goes back to your settings. So you, based on your signal to noise ratio desired, you are going to come up with the exposure. So what is the question is, what will be that? What is the minimum number of photons per projection that you need? How will you go about, right? So first and foremost, you are given a requirement for SNR in dB, but what we derived in the previous slide, you had SNR as a ratio. So first thing that you can do is convert this dB to ratio. How is that done? Oh, 20 log of, right, SNR log base 10, right. So so first thing you can get SNR alone, not in dB. What will be that? If it is 20 dB, right, right. So this will be the ratio. So that will be log of 10 by 10, 20 log of 10 by 10 in dB. So if it is ratio is 10, log 20 log base 10 of 10 will be 20 dB, right. So SNR will is 10. Okay, so I know my SNR. What do what else do I know? Oh, I need to get number of photons per projection. Okay, so I know my SNR. So that is signal and noise ratio. So I have some formulation for noise, right, sigma square. I have some formulation that you can quickly look through in the previous slide. So I have that. Then of course this SNR is what? You go by your formula, you had C times mu bar, correct? C times mu bar by sigma of mu hat. This is what is the definition. So I have my C that is given. I have my mu bar that is given. What is that? Oh, we have some formulation for that, but that you can measure from here, from the given information. So if you can measure sigma mu hat, I can estimate sigma square. What is sigma square? Oh, that you can look into your formulation from before, right? So sigma square is 2 pi square by 3 your rho naught cube T by mn dashed bar. So look back to your previous slide, you will see this formulation. So I can calculate my sigma from here. So I can calculate the sigma square. So I know this. What else do I know? Oh, now I have the right hand side, several of which I know. I know M, I know T, I know cutoff frequency. This is just 2 pi square. And I know left hand side, so I can get my N bar. Okay, so you can go do that, but what is asked is, where is the photons per projection. So if I have D detectors, then I will have to multiply with the D. For one projection, if I get N, then I have to multiply with D. Okay, so you can actually work that projections per thing is N dashed into D. N dash you can get from here. So you can calculate this. Just go do this. It's not. It's just substitution after this. Okay, so you will get some number like 1.87 into 10 power 8. That's your minimum, right? Minimum number of photons. Okay, so the objective is not so much on the calculation, the details of how you punch the calculator, about how we understand the question, appreciate that, okay, if there is a requirement, constraint from the end user on the acceptable image quality, how do we work our way around, because this is important, right? Based on this answer, you are going to ask the technician to acquire the image so that you can make a diagnosis. So you should know the end requirement and how that controls the data acquisition settings. This is the important. So in the context of covering the physics, instrumentation and image quality, I hope you will be able to swiftly go back and forth and understand how to connect all the three concepts. Most of the time it will be from the end user, some requirement will be there, some from the image side. So how do we go from that and see if we can improve it? Is there a fundamental improvement possible? If possible, then how do we acquire that at a fundamental level? So the raw data itself you have to acquire using that insight, using that condition. Okay, so that's so much for our signal to noise ratio and how we can use the information of setting and your context of recon, right, to calculate those. So now what we need to do is artifacts. Okay, so we talked about noise, but in the image, artifacts are also distractors, okay, that confuse the doctors from the actual object that they are trying to understand. If there is something that is distracting them, that is a no-no. So it's not a noise per se, but then it is a distractor. Okay, so it has to be reduced. So where all can artifacts come from? So in the process that we have done so far, first and for very easy to spot from our backgrounds is, oh, your discrete location. So the continuous function, so your distribution is continuous, right? But then I am making these measurements at discrete locations. In fact, I am doing two discretizations. One is the view angle, the other is the detector, the number of detectors, each one is separate, right? Along the L, it is discrete. Along the view angles, that is also discretized. So we already saw that. So how do we arrest that? So that is going to be your sampling. Whenever you have a sampling, you have to worry about aliasing. So how do you reduce this aliasing? You have to do, right, you have to do anti-aliasing filter. So in some sense, aliasing, if you are not sampling, if you are sampling less than the Nyquist rate, what is that? Twice the highest frequency content that is there, right? If you are sampling any less than that, you are going to get aliasing. That means what? Oh, your high frequency content might be wrapped into your low frequency. So you might, right, that will be the effect. So how do you avoid that? We need to do some anti-aliasing. So in this case, okay, so that means highest frequency. So the highest frequency, if you can apply this filter with some cutoff f max before you right, then you sample, then you are ensuring that that wrapping around is not taking place. So in our context, we were talking about number of projections, right, number of projection angles. So if you actually you can do this. So you throw some angles, right? You start with it, you get several projections, but then in your sinogram, right, you have all the angles. Just throw some angles. Do the reconstruction using only say every other step size or every fourth step size, and you will start to see the effect. Okay. So what do you mean by effect is you will vividly see this as a streak artifacts, right? You will see it won't be smooth, it will have lines. Okay. So you will see streak artifact. In fact, we will just show the image and you will recognize the streak artifact, but from before also we did this, but now what is expected is when you see that, you know where it is coming from. First time when we showed streak artifact, I said we will cover it later, but now hopefully you should be able to visualize the effect and say, I know where this is coming from, this is because I have discretized. So if I go back and change the number of angles, I should see the streak pattern changing, right? So you should be able to do that. Of course, in some sense already the detector, right, because it is an area detector, it is not a point detector, it is averaging out. So it is already having some effect implicitly, some pre-filtering is happening. Okay. Averaging is kind of your low pass, right? So it is already doing that to some extent. So here is a example of the variation of your number of projections, right, and samples per projection. So you can notice that even this is actually pretty you see one object here at the center, which is supposed to be the case, but you notice this star, right? So you can have this star artifact, people say. And in fact, when we talked about also, we talked about when this can happen, when you have sampling, undersampling, but we didn't really tell what it is. Now you know. Undersampling means in the context of either you can undersample in the views or you can undersample in the number of projections in that views, right, number of detector elements in that views. So either case has its own effect, and you see the aliasing when they say, okay, you can see the effect. Okay. So this is streak artifact. Then what are the other things that we talked about before? Oh, this is streak artifact due to sampling, that is one effect. What is the other effect in our recon we assumed? We assumed something about the energy. We used monoenergetic. In fact, when we sent energy in, we already said, unlike projection, in CT we are going to set hardened beam. What did we mean by hardened beam or beam hardening? That means the narrowing, right? That is what we said. So we said that when you do beam hardening, the spectral spread is reduced, you give only a narrow, and therefore monoenergetic is fine, or at least reasonable, and therefore all our reconstruction algorithm used this assumption of monoenergetic, right? But then that is not entirely true, because beam hardening can also happen after you do all that and you send it into the body. What you get at the detector, right, it is still, the beam hardening is also happening, but then it can be amplified depending on what material is on its path. If you have a strong absorber, right, so then strong absorber at that frequencies, then you are going to have behind that part, you are going to have a different spectra. So what enters is already a hardened beam, but then due to the interaction, the energy is lost, right? But then if you have some strong attenuator in the path, those locations you can have attenuated effect, right, and that will kind of or what preferentially absorbed, that we know. So this could actually come back into the image. So reconstruction algorithm, we assume this, but when you have effect of the beam hardening showing up, then the artifact results. So typically where do you have these effects prominent? Okay, we talked about bone. So it depends on the location, for example. So if you take a head scan, you have a bone skull and then you have soft brain, right? So the attenuation is kind of different there, and therefore when you have something like this, the amplification or the hardening of the beam is drastic because of the bone that is hitting, and you have to penetrate the bone before you go into the brain, right? So whatever you send from out, which is supposed to be beam, hardened beam, compared to your projection radiography, it's already a hardened beam, but then when it goes through the skull, your bone is attenuating far more, and then you get the, behind that you get your soft brain tissue. So in such cases you have lot more predominant effect of your beam hardening artifact. So this is kind of a tricky artifact. Somebody who is working in the domain, they have done a lot of scans, they understand the organ, they may know, so they have to work on the dose, they have to try to reduce this. Okay, so they know what to interpret, what is a beam hardening artifact. So this is a tricky artifact though, right? So you could get this artifact in other regions also. I mean, this is a head scan, but you could get it at other locations also, right? Abdomen, for example. So it depends. So if you have a bullet, right? I mean, somebody gets shot, if there is a implant, it's a different material. So there you have to be very careful in its interpretation. Beam hardening artifact, and so your sampling, beam hardening. What else did we talk about when we talked about introduction to artifacts? So when we come to CT, these are very prominent, and then you have a detector. Regular electronics is there, electronic drift, all those things are there, but more importantly we have detectors. If one of the detector goes bad, right, what does that mean? Oh, that means it is whatever, it is going to always have a zero value, right? What does that mean? Oh, physically that means everything that came in along the line of sight is attenuated, absorbed by the body. So it is going to say a very high attenuation value will be projected along that path. Okay, but then what is the thing? Oh, you are going to rotate, right? Different angles you are going to do, but the detector is a malfunctioning detector. So every rotation, wherever that detector is there, along that line of the detector, it is going to project back and say this is high attenuation. Everything is absorbed in the medium, right? So when you organize it in theta and sum, what is going to happen? You get what is called as a ring artifact. So the size of the ring, right? So it's very more prominent here. I think you can see the effect. What is the so the size of the ring, for example, could tell you, the radius of the ring could tell you which element from the isocenter, right, center of the detector, right? You have the source, you have the center, and then its width. So if a detector is gone bad, the location of the detector from the isocenter, right, from the center of the detector, that radius you will see the ring. Okay, so ring artifact is again something that they can spot. I mean, it's not really a pattern that is there inside. You can have, so not a pattern, but at least one ring, if it is there, is it a circular lesion or some circular growth, or is it because of malfunction? Again, domain expertise and experience comes into picture, but this is kind of a very, if you get nice circular symmetric, all likelihood it is going to be because of your reconstruction algorithm. You have projected it back based on the theta for full 360 degrees, so you are going to get likely that it is an artifact. Nature is beautiful, but maybe it's too good to believe that you have a perfect concentric circles that are coming in the object. Okay, again, some amount of domain knowledge is important, but these are fairly understood well. Okay, so one another common thing is your motion artifact. So we talked about different generations, and the time also I kind of cautioned you. So if you have motion during the data acquisition, you cannot do much. right? You are going to project that back, and so motion artifact is common. Most of the times you'll have to rescan. Okay, there are subtle times, for example, so here for example you have to rescan, but the advantage, but it depends on, so it's a anatomical image if you want here, right? You can ask, put a fixture and have the head stable. But for example, if you are going to do a CT of your heart, right, it is always going to move. There is going to be, so one is fundamentally you have to do high frame rate, but after that what do you do? If you want to see some dynamics that is moving much more than your frequency of temporal frequency, right, your scan frequency, what do you do? Well, say for example heart, what they do is you have what is called as ECG gating, right? So they can have the ECG and they can collect the data and then go back, synchronize it with the ECG and say, okay, every time, right, this data we got, next time also at that location only I will synchronize it with what they call as ECG gated. That is one common way they try to do it. So you do multiple acquisitions over different cycles and then go back, synchronize it with the ECG, which is very good temporal resolution, and then take only those frames that are all in certain time interval in the cycle that you want. Okay, so that is one common way they do too. So to reduce motion artifact, here vivid artifacts is fine, you rescan, but sometimes intrinsic, when you are really dealing with intricate organs where there is a motion, but you would still like to look at the image without motion because you want to measure the thickness of the valve, right? If you have blurring and the thickness is, because of the blur is certain value, you will lose out. So so there are critical applications where you may want to minimize the motion blurring, and the motion is not because of your outside motion that is controlled. It could be inside. Breathing you can hold to some extent. Heart is a good example. It is going to do its job. So motion artifact, there are ways to correct it, but this can be corrected at the acquisition stage. So to just summarize what we have covered in the whole idea module of X-ray CT, X-ray computed tomography, we started with parallel projection reconstruction, okay, and that is a simple intuitive paradigm to understand. So where we talked about back projection summation first, this is the intuition way, just project back the average sum, but then we kind of made it little more formal because the image were blurry. We started looking at mathematical correctness, and then we noticed there is a projection slice theorem, and that projection slice theorem was a Fourier method, but then we said this is not that popular. Most popular is your filtered back projection, but filtered back projection also, if you have to implement, you know, you have to do couple of frequency, go from Fourier domains back and forth. So more practical one was convolutional back projection. So you do your convolution in the spatial domain, right? So it's also filtering. Then we talked about fan beam projection and reconstruction. So here what the take home message was, it's very similar to what we had before. Only thing is, start to imagine there was 1 by d dashed square. So that adds a weight. So you start to think as weighted back projection, otherwise it's a back projection only. Okay, same filtered back projection, but you have one more 1 by d square term. So that is your weighted for the distance from your source to that point. Then we talked about image quality. In the image quality, we talked about blurring, and the blurring introduced due to your filtering, the non-ideal filter and the area detector. Not a point detector, there is a area detector, and therefore we introduced that as the blurring, that introduces a blurring effect. And so we talked about this and the equivalent filter that you can get for the blurring, we obtained using inverse Hankel transform, H of R, right. So, this is something that we did, and then we talked about noise. In the noise, we talked about not just noise in the context of differential signal to noise ratio, and we talked about how the factors, some of the factors that are influencing this to be the X-ray intensity, number of view angles, number of angles per, right, number of samples per angle, and your filter cutoff, anti-aliasing, and we also talked about different artifacts. Okay, so I think this is a, like I said, this is supposed to be a introductory material for this module, because we are covering different modalities, but what we covered here is fairly at a level where if you understand this and you have some self learning motivation, because you are working in this area, or you plan to work in this area, or you have worked with some image processing of CT, and you would like to understand more, I think you will be able to catch up to the state of the art in quick time after you start to work on this, do some programming of implementation of the recon. That will be a suggested strategy to master this material. Okay, so thank you.